Say I have a projectile that I toss into the cloud straight upwards, and we have somehow a function that tells us the velocity of that projectile at any given time. Notice that the velocity changes as time changes. And I want to estimate how far the projectile will rise during the first 3 seconds. Okay, so in order to tackle some of these, I'm first of all going to assume that we barely know any physics, because this is actually quite easy if you know a little bit of physics. This is, of course, gravitational acceleration, 9.8 meters per second squared. And this would be initial velocity right here. But again, this is not a physics class. Let's assume all we know is that we have some sort of machine here that will tell us the velocity of that projectile, which is tossed straight upwards. In other words, it only has vertical motion. So this would be the velocity of the projectile purely up and down. This tells us the velocity at any moment in time. And I want to know how far the projectile will rise during the first 3 seconds. Something to remember is that, or something to recall, perhaps I'll start with this. I'll give a few equations that we should know intuitively. If I were to ask you what the velocity, rather I should say, the average velocity is over some sort of interval, what I would do is I would take the change in position and divide it by the change in time, okay? And better yet, if I wanted to find the speed of if I wanted to find the speed of some sort of object and it was in one-dimensional motion, what I would do is I would take the total distance traveled, I abbreviate that with total distance traveled, and divide it by a change in time. And technically this would be average speed, so I put that bar on top. Now, if I were to drop the average and say that v is equal to distance divided by time, this is probably something that we're all super familiar with, the simplest, but there's a huge assumption that we take here. With this formula, we are assuming this v is constant. So like I said, you might be tempted in here to just plug stuff into this formula. We know the change in time is 3, but then what are you going to replace v with? V changes as time changes. So this isn't going to work perfectly in our case, but what we can do is, first of all, this implies, of course, that the distance, by multiplying both sides by d, is equal to the velocity times time, how much time has passed, velocity times time. So what we can do to make this work is to not let that much time pass at the beginning. So instead of maybe waiting the full 3 seconds, let's just allow this projectile to soar for 1 second maybe. So I'll write that. Let 1 second pass. And check the velocity then. In order to do that, of course, we would simply compute what is v of 1. Well, that is equal to, okay, I'm putting pressure on myself here. We got 150.2 meters per second, maybe. I'll drop units like a bad physicist, but I guess like a good mathematician. V of 1 is equal to 50.2 meters per second. And let's just assume, well, since we know that 1 second has passed, let's assume, or I'll say this, instead of assume, approximate, because that's what we're asked to do anyways. Distance traveled by assuming the ball, I'm abbreviating projectile to ball, had this speed constant speed. Or I'll say this, had this speed the whole time. So what we're doing is we are making an assumption. We know that this velocity changes during the first 1 second, but it doesn't change as much as it would if we waited for 3 seconds. So let's kind of shorten it a little bit. So d, the distance traveled over the first second, would be the approximately equal to, I wrote an equal sign, I really don't want that. The distance traveled over the first second would approximately be equal to, using this formula right here, and assuming that the speed is virtually the same this whole time, 50.2, hello, 150.2 times 1, okay? Now, if we wanted to approximate as accurately as possible how far this guy travels in the second, what we would do is first add up how far it traveled in the first second. So we would have 150.2 times 1. And then add to it the speed of the ball at 2 seconds, right? But we've already collected how far it went, an approximation for how far it went during the first second. So I want to wait 1 more second and approximate how much further this ball went during the second. But what that means is I'm actually only waiting 1 more second. So I'm only going to let the time run. It's tempting to put in 2 right here, but I'm only going to let the time run for an additional 1 second. So I'm going to put a 1 right there. That is going to be equal to 150.2 plus, okay, so v of 2 seconds. I'm really making my job harder. I should have just made this 10 in hindsight. All right, minus 9.8. Let's go with... why is that the hardest thing? Okay, so that's like 196, 19.6. Or, yeah, 19.6. 160 minus 19.6 would be 160 minus 2140.4, hopefully. So this is how far it traveled during the first second. Let me maybe write this down. This is how far it traveled. And it's approximately how far it traveled. This would be approximately how far it traveled during second. All right, so what we're doing is we're letting time run here for 1 second, and we're just using a dummy, arbitrary testing point for the velocity and assuming that velocity is the same this whole time. So we just said, let's just compute the velocity at 1 second. Even though the velocity decreases from 160 to 150.2, what we're doing is we're somewhat abusively, I guess, saying that, hey, let's just assume that the velocity that whole time was actually just 150.2, and under that assumption, how far did it go? All right. And apparently it went 150.2 seconds, of course, or meters, I guess. Next, during the second of motion, we use a dummy approximation for the velocity by simply asking what is the velocity at 2 seconds. Of course, the velocity actually varies from 150.2 down to 140.4 along the second of motion. But let's just approximate by declaring that the velocity of that whole time was this 140.4. And that would mean, using this formula for distance, that the ball traveled an additional 140.4 meters during the second of motion. And of course, you can perhaps see where we're going here. Let's approximate how far this ball traveled. Oh, let's add it again. So d of 3 would approximately equal. So let's add these two. That should be easy for me. 290. .6. If we wanted to evaluate how far this guy went during the third time interval, what I would do is approximate using v of 3 and let the time run for that third second. So to be clear here, this represents the third second. The third second, like as in second of time. All right, what is v of 3? That's too difficult. 9.8 times 3, I'm going to do 98 times 3. That's 100 times 3 minus 6. So that's going to be 294, but move a decimal point, that's 29.4. But it's 160 minus 29.4. And of course, that is the same thing as 290.6 plus, okay, I'm going to subtract 30. Oh, this is embarrassing, guys. 130.6. And that is the same thing as 421.2. Okay, so our approximation here is by taking, I'll write this, by taking sample points at t equals 1, 2, and 3, we know an approximation for how far the ball traveled. Something to notice, overall, what we really did is we said d of 3, I'll just use symbols, is approximately equal to 1 times v of 1 plus 1, so that's the second point of motion, times v of 2 plus 1 times v of 3. And context clues tells you, hey, this 1 times all of this nonsense kind of looks like a delta x. And I'm just going to call it delta x, or I'll say delta t, of course. Change in t times v of 1 plus change in t times v of 2 plus change in t times v of 3. Okay, and this is equal to, of course, delta t times v of 1 plus v of 2 plus v of 3. And you should ask, well, this is, like we said, a gross amount or a gross approximation. And also what you should ask is, oh, wait a second, doesn't that kind of look like something we have done already? So, of course, you guys should be able to notice, or you should be able to graph this guy. So that's going to be a line with a slope of negative 9.8 and a y-intercept of 160. All right. So this v of t looks something like this. That is v of t. And what we just did, what we just computed to figure out the distance traveled, notice what this is this is 3 seconds, of course. And we divided this up into 3 pieces. We calculated v of 1, so this would be v of 1. We calculated v of 2, and then multiplied these guys by this length right here. What is that length? Well, that has length 1. Wait a second, that's super similar. Of course, we also calculated v of 3. Oh, I'm being silly, and I'm assuming the x-intercept is 3. My bad, guys. Let me do this again. The x-intercept is definitely not 3. The x-intercept is like something like 16-ish. All right. Let's try again. My bad, got ahead of myself. All right, let's do this. Let's try this again. I'm going to draw the same graph, but I'm not going to poorly label anything. So I'll do this instead. That's like 16-ish, like I said, but this would be t equals 3. And what we did is we computed these 2 time intervals. We computed the velocity at this time interval. So that would be, or excuse me, at this t value, that would be v of 1. The velocity at this t value, so this would be 1 and 2. The velocity at this t value would be v of 2. And the velocity at this t value, of course, would be v of 3. And then we assumed that, what we literally did is we assumed that this curve was actually flat this whole time. Now, obviously, that's wrong. But we just assumed, to get an approximation, that this curve didn't decrease like this. Let's approximate how far it went by assuming it was flat like this, because we know the formula for a constant velocity. For instance, if I were to drive 20 miles per hour for 3 hours, that would simply be 20 times 3 to find the distance, how far I traveled. So this length right here would be a change in time, and that would be 1 second. And right here we have 1 second and 1 second. And like I said, what we did is we had delta x times v sub 1. But wait a second. That is the area of this first rectangle. V sub 1. Delta t times v sub 2. Oh, wait, that's the area. Delta t is this length down here, or this length right here. In other words, 1 second. Delta t times v of 2. And, of course, this area right here would be delta t times v of 3. All right, so what we did is we said the distance traveled is approximately equal to, well, really what we did is delta t, 1, times the right-hand rule with 3 rectangles. Okay, that's absolutely huge. But that is approximately equal to the area under the curve. And we are getting really, really close to one of the most crucial ideas in all of calculus. Fundamental, I would even say. Notice how these guys are related. Something we remember from calculus, differential calculus, excuse me, is that if I were to grab a position function or a distance function, perhaps, and take its derivative, r prime of t would actually give us the velocity function. And then if I were to take that guy's derivative again, hopefully you remember this, that would equal, of course, the derivative of velocity, which is what I call acceleration. But what we just did, somehow, is we were given a velocity function, and we were able to extract some sort of information about the original position by starting at the velocity function. Going this way, it seems like what we have to do, well, what we know we have to do is take derivatives. But going this way, from velocity back to distance, it seems like we need to, this is so huge, you guys, compute areas. All right, so that understanding, I'm really kind of trying to hint us at probably the most fundamental, I keep saying that word, important theorem in all of calculus. All right. That's what we just figured out. Now, again, to come back here, if we wanted this to be a much better approximation, what we would do is just not let that much time pass. We originally let a whole bunch of time pass. By that, I mean 1 second. But if we don't want to, if we want our distance traveled to be much more accurate, what we could do is let a fraction of a second pass. That way, this velocity, a good way to put it would be this velocity didn't have a chance to change much because we're only allowing it to change over a fraction of a second, a very small amount of time, which means our velocity will not have changed much, which means that the velocity is approximately constant over shorter instances of time, which allows us much more freely and accurately to use this formula right here, which only works for constant velocities. So what we could do to make the distance traveled much more accurate, of course, is to increase accuracy. To increase accuracy, we increase the number of time intervals. In other words, allow much less time to pass over. And I'll write this so that, and I'll write this kind of in quotes because this is more like my mathematics. It's nothing super official. Velocity, but it's good intuition, doesn't get a chance to change much and is therefore approximately or kinda constant, so that we can use this formula, d equals velocity times t, more accurately, or freely, I guess. Accurately is better. But in context of the picture, because we like pictures, all that means is I'm going to introduce more rectangles. So if I only allowed, for instance, let's go here, like this much time to pass instead of the full 1 second, then this would be my sample point. I call it a tag. That would be the tag. We'll develop that later. And then if I only allowed this much more time after that, this would be the sample point. And the smaller these time intervals are, the more this velocity function approximates a constant curve, okay? Much less change this way if I shrink the time interval. Constant functions do not change in the vertical direction at all, so to approximate constant functions, I can shrink the time interval so that this change in velocity shrinks towards zero. Man, the stuff I'm saying right now is like literally the essence of calculus. Sorry, I'm kind of rambling. This is more like my thoughts about this idea, and I'm trying to kind of get us to see one of the core ideas of calculus. I could be not coming across to anybody, but that's okay. We'll discuss it in person in a little bit more detail. But okay, so to increase accuracy of the distance traveled, we increase the number of time intervals. Notice that all these pink intervals, that's going to increase a lot more time intervals. But I don't need to go that far. I'm only wondering up to 3. But the time interval itself shrinks because they all have to fit into this 3-second interval. But notice what we will end up computing. Okay, that was horrible. Is an approximation for the area under this curve. Okay, so huge thing, and I'll end with this. And I've kind of already said this. Distance traveled from t equals 0 to t equals 3 seems to be the area under the curve of the velocity versus time graph. Okay, so here's a conjecture. And we could actually, check this out, you guys, this is a shape that we know. So if I were to take this pink shape right here, that's simply a trapezoid. What we actually could do to find the literal distance traveled is simply compute the area of that trapezoid. So that area, that pink area, if I were to fill this out, is actually exactly equal to 1/2 the height of that trapezoid. That will be an interval of 3 right here, times the sum of these two bases. So that is going to be 1/2 times 3 times the sum of the two bases, which will be f of 0, which is 160. Not f of 0, v of 0 plus v of 3. And of course, I think I've calculated these already. I hope I have. Yeah, so that would be 160. Oh, sorry. That would be 3/2 of 160 plus 130.6, I think. Okay, so that's the same thing as 3 times 80 plus 65.3. And that is, okay, so this is equal to 3 times 145.3. Okay, what is that? That's approximately equal to, okay, so it's going to be 0.9. 45 times 3. Oh, gosh, that's 27 times 5. Why is that the hardest thing? 135 plus 300, so 435.9. I could be wrong. Oh, look, let's see our approximation. That's not too bad. And was it an undercell? Yes, it was a little bit. And we expected these rectangles to be undercells. Okay, so our guess is actually, if this conjecture that we just made is correct, we haven't proven it's correct yet, we will, then the distance traveled is actually exactly. I'm not approximating anymore, but we have to assume that our conjecture here is actually correct. 435.9 meters. Okay. All right. So what was the big thing I wanted to say? Okay, the big thing I wanted to say is position relates to velocity. If I were to go this way, derivative. And because we are Calc 1 graduates, that really means slope. And going from velocity back to knowing something about velocity, and going back to position, that seems to have to do something with area. Okay. This, I don't know how to emphasize how important that is. That was a horrible box, but that's what I've got. All right. I wanted to do one more example. Average value. Do I have time? I really want these guys to be like 30 minutes long. Maybe I'll save this one for another time. Okay, so this is average value. I don't think I ask any average value questions on the quizzes, so I feel okay putting this off to a different time.